Let's see. When does it due? When does it due?
Yeah, 1 week.
Less than a week. Oh, a week. Okay, a minute less than a week. Okay. Any questions or issues on the project?
Are we integrating the type checking into it for this?
Yeah. No, the type checking is just does that identifier exist or not?
Okay.
Has it been multiply defined? Has it been used without being defined? That's it.
Okay. All right.
And there are test cases that have those error messages.
Variables could technically potentially be more than one character long.
Yeah, for sure.
Alright, so write to for that possibility.
Yeah. So identifiers have this. I didn't talk about it too explicitly, but this is the regular expression for identifiers. It has to start with a letter, and then 0 or more letters or digits after that. So I kind of only said this subtly, but assuming that you're matching the longest possible string when you match these. So rather than, if you have the identifier XYZ, that's not 3 identifiers. It's the longest possible regular expression you could match. It's greedy. And I didn't make this super explicit, but that's the assumption that I'm using. So that kind of leads me to this interesting problem here, which is what if I have this program? I say int followed by the identifier integer, and then the next line is integer equals 0. So first of all, is this valid? Simple C? Yeah, it's valid. According to me, it's valid. Assuming with that we take, we match the longest pattern for this regular expression, then int will match the keyword for int, and integer will match the identifier regular expression. There's another little wrinkle here that currently the program specification, the grammar specification says 0 or more declarations followed by 0 or more statements. So for those of you who are reading one character at a time, notice that the beginning of these two lines are identical. They both start with int. So if you're reading one character at a time, how are you going to tell the difference until you get there? What can we do?
If the T is followed by a space or not.
Okay, yeah, if the T is followed by a space or something that's not part of int, that's one way to do it. Any other way? Who else? Did anyone else try to tackle this problem? Yeah.
So I have it set up where my main does statement and executes declarations and then statements, and then it's got a flag. And it goes through and it reads in one character at a time, but it continues until it doesn't see something that's a digit or an alpha. And then it compares it against known keywords, such as
Okay.
Since we only have int declarations, it's just going to say, is this an int? And if it does, it just kicks back out, and then it immediately moves to statements. That's the last time it ever looks for declarations at that point.
Mm-hmm.
So, and then for the other parts, it's looking for print, it's looking for read or whatever, or it's just going to read in. If those don't match, it's just going to keep reading it until it pulls in.
Yeah, I think that makes sense. That's actually the solution I'm going to propose. Yeah, go ahead.
All of the alphabetic tokens cannot be followed by another alphabetic token, like a space or another symbol.
Right.
You can say if the next character in an alphabet is alphabetic, then continue reading that if it's a string or possibly just a longer token.
Yeah, I mean, it's exactly the same idea. So if you read int and there's no alphanumeric characters after it, then you know it was the int keyword. I think for those who are writing this in the style where you've got a function called declaration that's supposed to read a declaration, and then you're using fgetC to read each character of the declaration. That's a little tricky because your production for program has to kind of know ahead of time. Like it has to know whether you're still reading, while not done, process or start parsing declarations. Oh, don't have indenting. Let me make this. Let's give some syntax highlighting. This is like conceptually how you would write this production. But the problem is, how do we know what done is? That's the problem. So in all of these schemes, yeah, you can like assume it's a declaration and then somehow back out, but then you've already read, potentially 3 characters. And F ungets C, as I kind of maybe subtly mentioned a couple weeks ago, only will work for 1 character. It's only guaranteed by the specification to work for 1 character. Yeah. Yeah, you could do that. You could use seek. You still have to kind of keep track of how far ahead you went, but that could be an option. Yeah, I don't see why that wouldn't work. Yeah, I don't see why that would work. So it's an offset, so you could keep track of how far you went ahead. Yeah, that would work. That would work. You could do that. You could also do a complicated buffering scheme where you do your own buffering for fgetC. But I think probably the easiest approach is to merge the productions for declarations and statements. So rather than making this clean distinction between declarations and statements, you could have a different version of program where you just always read an identifier first. So the first thing I do is read an identifier. So it's going to be like my ident. And like your classmate pointed out, all keywords are also identifiers. And the Dragon book points this out as well. I don't know if I said this very explicitly in class, but one way you can handle this is just treat keywords as if they're identifiers, because the regular expressions for them are the same. Identifiers is a superset of all the keywords, at least in our language. And so you could always read in an identifier and then do use string compare to see, that this is not valid C, but you can use string compare to check whether the ident is yeah. Which question?
What about the tokens like plus and minus, which are not alphabetic?
That's okay, because we know that all declarations, at least, begin with an identifier, and we just have to kind of merge declarations and statements. It's a little fuzzy. I'm not doing this in a very principled way, but you could make the parser a little easier to write by doing that. Now, if you had done the approach where you lex first and just get an array or a stream of tokens, then this problem kind of goes away, because you already know whether it's an int or an identifier ahead of time. And then you can write your parser like this with just using a look ahead. So, like while next token is int, do that. Otherwise, while next token is like not EOF, read in statement. That's how you could do it. But if you sort of merged your lexing and parsing where you didn't have a separate distinct parser, you need a way to determine this condition. And so, yeah, there's lots and lots of ways to solve it. You could use fseek. You could do your own buffering. You could write declarations so that there's some feedback that says, hey, I failed to get a declaration, and give some information in the return value that can help you start parsing the next statement. But yeah, there are many, many ways to solve it. So I didn't want to kind of constrain your solution space. I kind of wanted you guys to be able to explore for yourself different solutions and see what the trade-offs were. So it's pretty hard to define the best way. There's a way that I think would be easiest for me. But there really isn't a best way. There are trade-offs between the different approaches. And as you go along, you'll see what the pain points are and refactor. So one thing, this is not a software engineering class, but one trait of any good software engineer is that rather than when you notice a problem in your architecture, you notice a problem in the code, instead of tearing it down and rebuilding, you can actually change the architecture of your code without throwing it away. This is unlike a building in the physical world. You can't really do this in the physical world. It's very hard. Maybe a little bit you can do this, but in the programming world, you can completely change the underlying design of your code through refactoring. Doing renamings and pulling out code. And there's actually books on this. You can read like Martin Fowler's book on refactoring. And it's, what's that?
Just book.
A backup?
Yeah.
Well, you may have added features that if you have a backup, you're going to undo those features.
Well, I mean, you might just have a copy made before you start editing things in case you realize,
Oh.
oh no.
Well, that's what Git is. Guess what? That's what Git is. Git is version control, right? So if you go down a path that is wrong, then you can always revert your changes back to some previous state as long as you're making commits. That's what version control is for. In fact, it also allows branching where you can have, instead of having a single line of commits, you can fork your commits and make your changes kind of speculatively and then add them into the code base once you finish them. Yeah, so git branch, we'll do this. And you can just Google it and they'll give tutorials on this. But anyway, yeah, so this was one problem that came up in office hours. So you can kind of do it this way, where if I put this into a while loop, so this is actually a slightly different grammar where it looks like this. So this is as opposed to the original grammar, which is declaration star followed by statement star. So what's the difference here? Is there a difference? Are these different? Are these identical? Yeah.
Well, the declarations for statements, it doesn't necessarily mean that all declarations have to come before statements.
Yeah, that's exactly right. So are these, what's the set intersection? Is there a superset? Is there a subset here? What's the relationship? Yeah.
With the program prime, you could have declarations or statements in any order following each other.
Right.
But with the program, you can have 0 or more declarations, but they will always come before any statements you make.
That's right. Yeah. So are these languages? So the languages are not equivalent, but yeah.
Program prime is superset?
Program prime is a superset. So in other words, all elements in this set are in program prime. And you can probably sit down and prove that if you're interested. But I sort of promised you that I wouldn't give you syntax errors. So I wouldn't give you a program inside of program prime that isn't also inside of program. So you can kind of do this as a little hack. And because it's a superset, any program I give you will only be in program. But in general, it's a superset. So technically speaking, you should reject programs from program prime that are not in program. But to make it a little easier, go for it and do this for your assignment. Questions on this? Questions on this problem? So hopefully this is a little clear. I know I didn't make it super clear about the lexer, but my assumption was that you read the longest matching string in the input, which is something, that's something you have to make formal, that I have to make formal. And I did make it super formal when I did this. Okay, questions on this? Questions on project 2? Yeah.
Would there possibly be a situation where you might say something like int x equals 5, x equals x plus 5?
Oops.
So so there might be a line where
int x.
Where you set
what was it? Can you say it again?
Int x equals 5. X equals x plus 5. So something where we're going to have to load to a variable and then store it back to itself.
Yeah, absolutely. Absolutely. You'll have cases like this. Yeah. You can definitely do this. Just like in C. So he's just asking, can I have an assignment where I use the variable itself?
Or I can essentially have an x plus equals.
Yeah. This is x plus equals is syntactic sugar for this. Yeah.
Can you use
Uninitialized variables?
Yes, like where you had that, you didn't.
Yeah, if we did this. Yeah, so it's technically undefined behavior. I don't remember if I wrote this very specifically, but it's undefined behavior, and it'll be allowed to run. But you can add checking to make sure. But I'm not going to give you cases where you have syntax errors or undefined behavior beyond those that the type checker is supposed to catch. So you only have 2 types of errors to catch, and that's undeclared variable and multiply defined declarable at this point, for project 3. Okay. Other questions?
Just to make sure, we're not going to have something like x plus equals 5, right? That's not part of our grid.
No, yeah, it's not part of the syntax of the language, so you won't have it. Give me 1 second. Let me just notate these. I want to make sure these are in the documentation, and also I'll put these down. Okay. Okay. So let's move on to the next section. So this is all the content for project 2, and so I'll leave you guys to finish this up over the next week. And so we're going to start looking at the stuff for project 3 on control flow. So first, I'd like to just go over what control flow looks like in simple C, and then we'll look at the grammar for it, and we'll look at some of the issues with parsing that grammar. So as before, I've recommended that you get the parsing correct in your program first before trying to do code generation, because if the parsing's not correct, the code generation probably won't be correct. And it's kind of hard to do these at the same time. So you can first kind of like get these mutually recursive parsing algorithms working, and then add code generation to it. And we'll do that over the next week. But today we'll just look at parsing for this new grammar. Okay, so as you probably all hopefully realize by now, if statements encode decisions in your program. You set up the conditions in Boolean logic, and then the instructions guarded by that logic are only executed when those conditions are actually met. So if we have this program in simple C, where I declare the variable x, I read it in from input, and if that x is equal to the integer 10, then I print x. Otherwise, I print 0. And yeah, so the way this works is that the condition here is specified between the parentheses for the if statement. And if that condition holds at runtime, then you execute the instructions in the first branch. Otherwise, you execute the instructions in the else branch. So a little question. What are the conditions under which the else branch prints in this case?
X is not equal to 10.
X is not equal to 10, right? It's the logical negation of the if statement. Okay, yeah. Yeah, any questions on this? Should be pretty straightforward. I think you've all written thousands of conditional statements, right, at this point? So one useful way to look at this, I don't know if you guys have seen this yet, but we can represent this flow of control in the program as a flow chart. So has anybody actually used flow charts, like in, I don't know, engineering or, used flow charts? Has anyone seen this before? Has anyone actually done this? Flow charts for if statements? Who's seen it? Who's seen flow charts for control flow? Oh, interesting. Who's not seen it? Interesting. Okay. Yeah, so you can think of the flow of control in your program, and by flow of control, it just means which statement comes next as you run the program. You can think of this as a flow chart that describes all the possible decisions that your program will make through the flow of control, through the course of execution for some given input to the program. So it might be kind of obvious, but when you have these two different branches, every time you run the program, only one of these branches will be executed. That should be pretty obvious, right? Only one of these branches will be executed for any given run of the program. And the point of the conditional is to account for different inputs and to have different behavior depending on what the inputs to the program are. So ultimately, all of these values, their variation comes from the fact that they are inputs to the program. The program doesn't know ahead of time what the value of x is going to be. And so the condition statement allows us to change the behavior based on what the inputs are. So to see this in flowchart form, we can turn each of the pieces of straight line code, that is code that has no branching in or out of it, we can turn that into a block in our flowchart or a node of our flowchart. And we can turn all of the conditional tests of our conditional statements into a branch in that flowchart. So here I just use a little question mark to say I'm asking, is x equal to 10? And I can represent the two different branches, the two different following instructions that will happen at runtime with two different edges leading to the blocks within those branches. So if x equals 10, I put the yes branch on one node and one edge, and I have print x for the yes side of that, and print 0 for the no side of that. Make sense? Questions on this? Control flow is a flow chart. Pretty straightforward, right? Okay, so let's look at while loops now. So while loops, as I'm sure you all know, the instructions repeat until some certain condition is met. And we can actually think of these as unconditional branching, where you have a single if statement inside of unconditional branching. So let me go through this to see what that means. So in this program, I'm declaring two variables, x and y. I'm reading in y. I'm setting x to 3. The condition of my while loop is not x equals 0. Then the body of my while loop is y equals y times y, and x equals x minus 1. That's the body of my loop. And then at the end, I print y. So look at it for a second. Who can tell me what this program does? Yeah. Does it cube a number? Yeah, that's what I thought at first. But actually, no, it doesn't cube a number. It cubes something. Unless I'm wrong.
Oh, I think it's more like to the ninth power or something.
To the ninth power? Who says cube? Although I just said no, it wasn't cube. Who says to the ninth? It's pretty tricky, right? It's pretty confusing, isn't it?
27.
Should I run
Y
it?
to the 8th.
Y to the 8th? Who says y to the 8th? Who agrees with that? Getting more agreement. Who says not y to the 8th? You can prove it's not y to the 8th.
The first loop it's going to be y squared, and then y is currently y squared, so y squared times y squared is y to the 4th, and then the third loop is going to be y to the 4th times y to the 4th.
Yeah, let's go through it then. So I think this is an interesting one. I thought this was y cubed at first too when I wrote it. I was just making a random example. So let's look at it. Oops. So x equals 3, y equals whatever, while not x equals 0, y equals y times y, x equals x minus 1. When looking at code, I like to run an example through it. So let's say y equals 2. Let's say y equals 2. All right, so y equals 2, x equals 3. That's the state when we enter the first iteration of our loop. So this is good. We can actually walk through kind of like rigorously, or not rigorously, but like in tedious detail how we can actually show the execution of this loop in simple C. So here's the state before the first iteration. And then we do the condition. We say, is this condition true? Well, it's, 3 equals 0, not 3 equals 0. So yes, this is true. And now we have the state mutation due to the body. So we've got y equals y times y, x equals x minus 1. This is 2. These are both 2, right?
Yeah.
These are both 2. So what does that give us? 4. So y is 4. This is 3 minus 1. So what does it give us for x? 2. All right. Now we're reached the top of our loop iteration again. So let's test. 2 equals 0. Yes or no?
Yes.
This is true? Yes, it's true. So now we've got y equals y times y. That is now 4, right?
Yeah.
4. So what's 4 times 4?
16.
16. X equals 2 minus 1. That's 1. Back to the top of our loop. 1 equals 0. Yes, that's still true. So now we've got y equals y times y. Y is 16. 256. Good, knowing your binaries. And now we've got x equals 1 minus 1. That gives us 0. We're at the top of our loop, and I've run out of space. So not 0 equals 0. What does that give us? False. I'll say no. Okay, so this is actually good practice when you're trying to understand what code does. You know, of course it's best to have the general solution, and there are like techniques for doing this, for like proving in general what a piece of code does. But you know, as a working programmer, it's very useful just to be able to like run code in your head, and you should all be able to do this. It's really, really useful for debugging. You know, debugging is not fixing the code. Debugging is fixing what you think the code does. Because what is a bug? A bug is a difference between what the code is doing and what you think it's doing. The code is not wrong. The code is not a human. It can't error unless, you know, some sunspot causes the processor to like flip the wrong bit. But assuming that the hardware is working correctly, your code is never wrong. It's doing exactly what you told it to do. The problem is the difference between what you think it does and what it actually does. And so being able to like sit down and trace through a piece of code is a really important skill to have. It's actually almost not even a skill. It's actually really mechanical and tedious to do. So the real skill is getting through the boredom of that, really. Okay, so now we can see an example of running this code, what it is. Maybe we can generalize a little bit now. So what is the relationship between 2 and 256?
It's to the 8th power.
It's 2 to the 8th power. Yeah, it's 2 to the 8th power. And we can kind of convince ourselves of that by seeing that whatever the original y was, so if we had y0 here, let me use a different color for this. We had some y0, whatever it was, at the first step, y1 equaled y0 squared. And the second time we did this, y2 equaled y1 squared. The third time we did it, y3 equaled y2 squared. And as long as we can convince ourselves through looking at x and its condition that it only runs 3 times, then this is our final value, and we can just, you know, use basic algebra to solve for this. So what does that give us when we solve? y3 equals y0 to the 8th, right? So this is a little bit more like formal verification. There is actually a course on this. Dr. Levins is an expert in formal verification. You can actually see how you can prove what programs do in general for all possible inputs. It's a pretty impressive thing to be able to do. And with static analysis, you can actually do this automatically in some cases. Okay, all right, I think we resolved that. So it's equal to 2 to the 8th. Or whatever y is, y to the 8th. Okay, questions on that? So that also kind of gives us an intuitive idea what the semantics of, you know, variable assignment is. So you can definitely assign variables to themselves. Assignment is really just computing the right-hand side and then storing whatever the right-hand side is into y. That's what we did in project 2. I don't know how explicit I made that, but I think in the code generation pseudocode I gave you, that should have been pretty explicit. Okay, so as I said before, you can think of a while loop as really an if statement inside of an unconditional branch. So I think you all remember branching in CDA, right? You've got conditional branches and you've got unconditional branches. The unconditional branch will just always jump no matter what the conditions of the machine are. It'll just always branch. And here I've represented that using a goto. So who's actually used goto in C before? Actually used goto? Who knew C had goto? Oh, okay. Who was trained that goto is considered harmful? Oh, okay, that's good. Okay, that's good. But you can still use it. It's there in C. You can use it if you want to make spaghetti code. But I've sort of what you might call desugared the while loop into an implementation that doesn't use while. It just uses goto and if. And so this will kind of help you as you generate code for this. in some sense, we're kind of desugaring what while means into simpler components of a language. LLVM doesn't have as much expressivity as simple C, and this is kind of one step, a different way to look at while, how you can implement while using simpler parts of the language. So here it's basically the same thing, except instead of a while loop, of course, I have an if with the same condition. The body of that if is here, and the go-to loop just always goes to the top just before I test the condition. So it doesn't go to the top of the program. It doesn't go to the top of x equals 3. It goes to just before the computation that computes this expression. And so now you've all done, most of you, or some of you at least, have done project 1, and you've seen how expression computation happens. So this expression inside of the conditional, inside of the while loops parentheses, will be computed just like you compute an expression. Whatever the value of x happens to be at that time, you're going to pull it out of memory and run this just like any other expression computation. And we'll talk about that when we get to the target language and code generation, what that code will actually look like. Okay, so you thought you knew what a while loop was. So any questions on this? Now you know even more what a while loop really is. Okay, so the flow chart, just like any other control flow, we can represent while loops with a flow chart, a slightly more complicated flow chart. So let's go through it. Remember, these flow charts work. These are actually called control flow graphs. They work by taking all of the straight line code, the code that doesn't have any branches in or out, and turning that into its own node in our graph. So this prelude to our while loop here can be represented in our flow chart here on the right. The condition is by itself in a block, and we'll see why that's the case. This condition gets tested, and there are two possible outcomes. Either it's true, in which case the meaning of the while loop tells us that we want to execute the body and then immediately jump back and reevaluate the condition. So that's what's expressed here. We have the body of our while loop, and that unconditional branch is just represented with a back edge, another edge in our flowchart, back to the block that computes the condition. So this is why the condition is in its own block. Notice that there's no branching between these two blocks, these two nodes of our flowchart. There's no branching here, but because we have an unconditional branch that jumps back to the part of the program that computes the condition, these two are actually separate blocks in our flowchart. Okay, so that gives us our while loop, and if you look at these flowcharts, you can already see the structure of what an if statement looks like or what a while loop looks like. And we'll actually, later in the semester, talk about how you can automatically create these flowcharts. And actually, this is what modern optimizing compilers do. They automatically create these flowcharts in order to do different kinds of optimizations. But you can see that the while loop has a characteristic shape in our flowchart. And actually, if you're interested in security, tools that can decompile, that is, take the binary, turn it into source code, or turn it back into source code, will use techniques like this to try to discover what the original source code looked like, because while loops just have this characteristic pattern in flowcharts. So if we can figure out that pattern from the binary code, we can kind of infer what the original source code might have looked like. Okay, anyway, so if this condition is false, then the next statement that we execute is this print statement after the while loop. Questions on this? Questions on what this looks like? And you can see you have what amounts to an if statement within this while loop. If we had taken away this back edge, it would look just like an if statement, more or less. Questions? Questions on this? We'll go more into these control flow charts in the future. These are a little bit simplified, but we'll go more into this closer to the end of the semester. Okay, so what about for loops? So Simple C does not have for loops, but if you want to earn some bonus points, feel free to implement a for loop. This slide tells you exactly how. But if we don't have a for loop, can we still do a for loop? Can we still do the same thing, express the same thing that we can do with a for loop. Can we do that in simple C? So who says yes, can do that? Who says no, can't do that? Okay, that's good because I wrote on this slide how you can actually do it. So a for loop can always be rewritten as a while loop. So who's seen this before? Who's seen that you can always rewrite them? Oh, okay. Who hasn't seen it? Okay. Who doesn't want to admit they haven't seen it? Oh, okay. All right, then I'll go through it. So a for loop is just a syntactic sugar for a pattern of using a while loop. In C, at least, the for loop works by having 3 sections within its parentheses, all separated by semicolons. The first one is the initializer, the second one is the conditional test, and the third one is I don't know what it's called, but I don't know the name of it, but it's the thing that gets updated at the end of the for loop. And so here on the right, I've rewritten this using a while loop, highlighting in red the same pieces of the while loop, but now put inside of this while loop form, or the pieces from the for loop and surrounding the while loop in their respective locations to make the equivalent program. So if x equals 3 is what happens before the while loop. So it only happens once. If we look at our flow chart, that happens here before the conditional test. That's where that initializer goes. So it's only run. That's why it's only run once, because it's before the while loop. The condition, of course, goes inside of the condition for the while loop. And this piece of code, I don't know the name of it, happens at the end of the while loop. And so in C, we're used to just writing like x++ or whatever. But you can actually write any statement you want here, and the compiler will just plop it right here at the end of your loop. You can write anything. You can actually have multiple statements there, I think, separated by commas. I think that's the case. You can double check me on that. But you can write whatever you want here. It doesn't even have to update anything. You can write whatever you want. So if you look at like experienced C programmers code, they'll do all sorts of like crazy tricks using this for syntax. Okay, questions on this? Questions on for loops, while loops? So I'll leave that as a bonus project. You just have to add syntax for the for loop and generate code for it in the same way. It's a pretty simple one. Okay, so let me go to the still under construction project page for project 3 and take a look quickly at the syntax here. So the new parts of this, so let's see. So who can identify the new parts of this syntax compared to project 2? For those of you who really internalized the grammar, yeah. Oh, okay, that's a good pointed out. So now we have curly braces. This is compound statements. What else is different? Yeah.
Not expression.
Not expression. Yeah. Okay. We have not expression. That's our Boolean negation. Anything else? Yeah. We got while. Yeah. We actually have a bunch more statements. Yeah. A couple of if statements. So this whole section here is new. The not is new. Anything else?
The equals and an or.
Yeah, we've got some Boolean expressions here. So notice that I've just thrown these into the same expression syntax that we used for arithmetic expressions. And that's because, just like C, where is it? Just like C, we use integers to represent true and false, just like C does, just to make this a little simpler. So last semester I actually had separate types, Boolean types and integer types, but I decided to make it more C-like this semester. And so we're going to use just whatever the underlying machine's integer representation is for our Booleans. And just like in C, a non-zero value will mean true, and a 0 value will mean false, just like C uses. So because of that, I can just kind of throw these expressions in the same tree. Yeah.
So when we evaluate true for a non-zero value, should we just use like 1?
Yeah, you can use 1. So I've left this as, do I say this in the slides? So I say in the slides that it's undefined when you mix integer values and Boolean values. So that should be undefined behavior. So you're free to make it non-zero, whatever non-zero value you want. It'll just be undefined, and I won't give you programs where I mix those two. So I consider it undefined behavior for simple C. So yeah, you can just use whatever you can just use 1 and 0. That's probably easiest. Equality, then conjunction, and then disjunction has the highest precedence, except for parentheses, followed by multiplication, division, then addition and subtraction, then equality, then conjunction, and then disjunction. So that's, what's that? Oh yeah, mod, sorry. Mod is at the same level as I'll fix that. You'll have to, again, rewrite the grammar so that you have order of operations respected, and make sure that it's not, you have to do the left recursion elimination. But you should be able to kind of like skip those explicit steps and maybe just write. You can try to take a crack at just writing the program with this precedence correctly. So yeah, so the Boolean operations have lower precedence than everything else. The unitary negation has the highest precedence. And just like in C, and this is kind of like a confusing thing in C, at least confuses me, the equality actually has a higher precedence than and or in C, which is really kind of annoying. I always forget this, and it causes problems. Okay, so when we rewrite the grammar for this, how do we fit in these lower precedence operations? Where do they go in the grammar? Where does logical negation go? So before we do this, let me motivate this with a few examples of expressions in our language and see how this parse tree will look for these. Okay, so let's take our first example. Let me just write it down. All right, so we've got x plus y times z and y. And let me move this to the bottom. Okay. So what does this parse tree look like? We've got our program at the top. Well, actually, let's just start with the expression. So which of these operations has higher precedence? Let's do it this way. So which one has the highest precedence?
Times.
So times is the highest. So that's the highest precedence. What's the next highest precedence? Plus. And then that leaves and as the lowest precedence. So if we're thinking about the root node here, the root expression node here, which of these will be higher at a higher level? That is, this way is higher, and this is lower in the tree. Which of these will be the highest? Which will be the lowest in the tree? And will be the highest. Good, yeah, and will be the highest, because that's where the lowest precedence will go. Because if we're doing a post-order traversal of this tree, the lowest in the tree will be evaluated first, or the code will be emitted first for those. So then what's the next level of this tree? The plus, good. And then that leaves the last level, multiplication, good. Okay, so that's like my quick and dirty way of making this expression tree. So we know that plus will be the left child of ampersand. Multiplication should be the right child of plus. Is this right? Am I getting this right? So that means y will be the right child of ampersand. For plus, x will be the left child, and that leaves y and z to be the children of multiplication. Make sense? Does that look right? Any mistakes? Okay, so that's just an example of what the tree will look like. So when you're writing your parser, you can kind of confirm this as you can confirm with print statements to make sure that the order is correct. And this also informs what the grammar will look like. If you rewrite the grammar to include precedence, this will help show what the grammar will look like. So let's do one more of these examples. Let's let's do the third one. X and Y equals not A. Ooh, I used the wrong symbols for or B. Okay, so let's identify the precedence here. So what operator here has the highest precedence? What's that? The not. Good, yeah. Negation has the highest precedence. What's the next highest?
Equals.
Equals, yeah. So equals has higher precedence, just like in C. And then what's the next highest precedence? And has highest precedence higher than or, and that leaves or as the highest. So again, what is the first node, the highest node in our tree in terms of like the levels of the tree? It's going to be or. So we'll have an or here. The next one is the and. Next is equals. And finally, negation. So here's the root of our tree. We know that the or will be first. The right-hand side of the or is B. And the left-hand side will be ampersand. The left-hand side of the ampersand is X. And that leaves equals to be the right-hand side of it. And so what are the two sides of equals? Y and the result of the negation, which is A. Does this make sense? Somewhat? Make sense? Okay. Questions? Questions on this? Yeah.
So we're gonna start with like E in this case for our,
So what will your grammar look like, you mean?
yeah, like, you know, like we have E T prime. Okay.
Yeah, so this is the rewritten grammar, including, I think it includes, oh yeah, I think it has everything. So expression will now be expression or and expression captures, you know, unlimited number of ands. Equals is higher than and, so it's later in the derivation. And then that brings us back into plus and minus, term, and factor. And notice that factor, at least in the way I did this, the negation is in factor, just like parentheses. Yeah.
So, in factor, you have integer now instead of number. Is that
Oh, sorry. No, that's. Oh, yeah. That should be number. Sorry. I'll fix this. That should be number. And this should be actually the symbols we use. Yeah, it should be the same. So the only differences are these expressions, the first expression, the and expression, equals expression, and not. Those are the only differences in this grammar. Okay, questions on this? So yeah, you'll have to extend your expression grammar a little bit. It should be fun. It should be fun. Yeah. So, and I mean, I guess if you did the infix to postfix trick, you might be able to start here at add expression. That might work. You'll have to figure out how to do the factor, but that might work. I don't know. Yeah.
what do you mean when you say
Oh, so some students, instead of doing the recursive descent, they did the infix to postfix conversion and then somehow used that to generate code. I don't know what it actually looks like, but I think some students were afraid of the recursion, but you shouldn't be. Recursion is fun and easy once you get the hang of it. Questions on this? Okay, so just a little reminder about this trick for handling right recursion. So several weeks ago, you all had to rewrite the grammar, the left recursive grammar that has operator precedence, and rewrite that into a right recursive grammar. And the parser is much simpler if you just turn that right recursion into a while loop. So I talked about this a little bit, I think, last time or 2 times ago. So instead of having to call expression prime, and then expression prime has this long production, you can just have a while loop that says, while the next token is my operator at this level of my grammar, my expression can only be or between expressions. You can turn that into a while loop instead. And that'll just make the grammar easier to write. So questions on this? I think I went over this before. Do you have any new questions on this? Yeah.
So what we do with the expression prompt, is that left recursion?
That was right recursion. So that was, so let me see if I can review that briefly. So if I had, oh, now I need to remember what it looks like.
How would that like fit into the new expression?
It works the same way. So if I've got, let's see if I remember what this looks like. Is this right? I think this is right. Or no? It's there, right?
Yeah.
So we could kind of informally turn this into something that we can. I don't know if this is like any official syntax, but you can kind of turn this into something that looks like this. So I'm kind of abusing the syntax for regular expressions and context-free grammars, but all regular expressions are also context-free grammars. So you can kind of turn it into this grammar. So it avoids the right recursion here. So you don't have to make a new parsing function for that. You can just have a parsing function. Because we're doing recursive descent, we can do this. Instead of having a new parsing function for e prime, you can just implement clean star using a while loop. So you can just say term and then while, and using this plus as a look ahead. This is your look ahead. You can just keep iterating while the next token is plus. So it's really kind of like turning it into a list in your parse tree, which, like the context-free grammar doesn't really support in at least the Dragon book notation of it. So in the first version of the program, you'd have a function for E and a function for E prime, and the function for E would call E prime. And then here, you'd have your look aheads for plus and minus. Those would be your look aheads, and you'd call T followed by E prime. And so there's your right recursion there. But, oh yeah, and I think we talked about tail recursion. You can actually this is equivalent to having a while loop. So you can turn this into a program where you call T, and then while the look ahead is plus, you just call, you read plus, and then just call T repeatedly until the next token is no longer plus. So you don't have to do it this way. It's kind of a little hack that can make writing the parser a little easier. But you can certainly use the first approach, which is kind of more principled, a more like literal translation of the grammar to a recursive descent parser. Questions on this? Yeah.
So with this rewritten framework, would it not, so it supports like one or more plus, or zero or more plus, or zero or minus, but the original framework do like minus plus, and
Oh, you're right. Oh, you're right. You're totally right. So it should be, to abuse the syntax even more, it should be like this. Sorry about that. You're right. It should be like that. Let's get rid of this. Yeah, it's more like that. It's more like that. To abuse the syntax even more. So yeah, I didn't have a good way to write it in grammar. I just kind of figured out you can just do this. Just do that. I tried to express it in the grammar. There are actually parser generators that can take syntax like this. It can take this kind of syntax, like Antler, for instance. Can take basically a combination of context-free grammars and regular expressions on the right-hand side. But I don't know how to talk about that formally. Okay. So that's the Boolean expressions. I'll send out an update on the operators for that. So it's not it's the full description, and test cases won't be out until next week anyway, until this assignment's done. But I'll keep you updated and I'll update you next time on that when we talk about code generation. So let's look at if statements. All right, so there's 3 new statements. There's an if then else. There's an if then else. There's a while, and there's a compound statement. Whoops. Sorry about that. Come on. Okay, yeah, so there's an there's a if then else, there's a while, and there's a compound statement. So let's take a look at the parse tree for if statements. And we'll use this example here that I've conveniently written on a single line to confuse you. So we got if x, print 0, followed by if y, print 1, followed by else, print 2. So let's take a look at what the parse tree might look like for this. So I'll write this at the bottom. And give me 1 second while I copy this. Okay, so here's our piece of code. And the question is, what does the parse tree for this look like? So just to kind of refresh you on the grammar looks like this. We have the if keyword followed by the l keyword. There's a parenthesis, there's an expression inside, then a right paren, followed by a statement. And depending on which production you're reducing, that could be followed by an else keyword and then followed by another statement. So this is kind of like what you'd expect the pattern of an if statement to look like. We've got if keyword, else, parentheses. This is an expression of some kind, and this whole thing is a statement. That's what we'd expect. That's kind of what we expect, right? The pattern, the template for what our if statement looks like. Okay, so what does this parse tree look like for this one statement? We know we have some statement here. We know that there must be an if at the beginning of this statement. We know there's definitely an expression. I'm going to leave out some of the tokens here. And we know that there's a statement. So this is roughly what we have, right? We have if, paren, expression, statement. But what's next? Do we have an else here? Or do we have a nested if statement? Which one is it? Any guesses? Second one? Who says the second one, where it's a nested if? Who says it's the first one, where it's an else? Who has no idea?
The first or
Who thinks it's both? Yeah, you're right. It is both, actually, right? Because the grammar's ambiguous. The grammar's ambiguous. You don't know from the grammar, actually. It's just like when we had expression plus expression. There are many ways to parse it, right? And we as the language designer have to resolve this. We have to decide which one is the one we want to use if we want to have an unambiguous grammar. So yeah, you got it. It's ambiguous. I knew I think that was a joke. You're right. You're putting it up as a joke, but you were right. When jokes are right. Yeah. So this is another example of an ambiguous grammar, and kind of intuitively, the reason is that when we get to the end, when we're parsing, and we get at this point, and if you kind of remember what the LR parsing looked like, we make this finite state machine of every possible position in the grammar, and when we're here, we have the same prefix. We're in the same state of parsing our input. And so when we see an else, we don't know whether we've just seen this production or whether we're still inside of this production. It's because the parser doesn't know that the grammar is ambiguous. The grammar could be, you could have both possible parsers and they're both valid. Yeah. That's exactly right. You could make it its own production. Yeah. You could make it its own. Yeah, you could do that. That's actually one of the solutions to this. You can actually make its own production. Yeah, that is one of the solutions to this. But yeah, just be aware that this is the famous dangling else problem. That's how it's named in the Dragon Book. And it's just the fact that if you write kind of a naive grammar for if statements and you want to have an optional else for that, then your grammar is going to end up being ambiguous. And so when you go to write a parser for this, you need to do something about it. You either need to change the grammar or change your parsing algorithm. All right, so the dangling else problem. The problem is that if the next token in the input is an else, which production are we in? Do we reduce the production and match an if statement without an else, or do we say, okay, we're in the if then else production? And there really is this grammar, there's no way to resolve this. We as the language designer have to decide which thing we want the grammar to do, which thing we want the parser to do. So what I think all programming languages that have this problem do is they match the else that's nearest to the if. So in other words, given a choice at this point in the grammar, we always choose this. If our next token in the input is an else, we always choose this production. And that corresponds to the else matching the nearest if. So when you write, and you all actually know this kind of intuitively when you write in C, that if we've got a C program with nested ifs, we even, the Emacs will even nicely nest this for me. Well, let's just not even put these. Emacs will just kind of do this for me. It'll do the nesting for me. Well, I don't know why I did that. So Emacs will, let's get rid of these prints. Why is it? Oh, because I'm not in a function, that's why. So Emacs will already kind of nicely indent it for me. But if our grammar is ambiguous, we don't know where this else belongs. We don't know if it belongs with the first if or the second if. But by resolving this ambiguity, we resolve it so that whatever else we have, it always matches the nearest if. And this corresponds exactly to the nesting of if statements that you're all used to in programming in C and Java. And so this is actually how it's resolved. You can either, just like your classmate pointed out, you can either resolve this by making a new grammar production that only matches matched if statements. So here, this match statement production only matches the if statements that have an else branch and only allows matched if statements within its nesting. Otherwise, we have the unmatched statement, which matches either the if statement with any if statement nested, or an if statement that only has matching within its if branch. So it's a little confusing to work through. The Dragon Book will walk you through it, and we'll walk you through this and what the parsing will look like. It's a little unintuitive to look at, but I guess the kind of intuition is that statements can either have a series of nested matched if statements, or it can have a top level not matched if statement. It's kind of intuitively how to look at this. But you can read the Dragon Book and look at it this way. So this is kind of confusing to actually implement in a parser. So there's a second, easier method to doing this. So we can instead, in the parser, resolve this by making a decision in the parser to choose between these two productions and always choose the case where we have an else statement following within our, always choose the case where it's inside of an if then else statement. So we can sort of rewrite our grammar. You don't have to rewrite it this way, but this kind of represents the fact that we process the prefix of both kinds of if statements at once. So if we have our statement can expand to an if statement. Our if statement can expand to the if prefix and an optional else statement. So this is, in the Dragon Book, they call this left factoring, where now both of my original productions have been combined into this common prefix, this if prefix. So we've got the if branch part of this. And this else option captures the fact that it can either be followed by an else and a statement or by nothing. So this alone, and I'll leave you to kind of contemplate this on your own or read the Dragon Book. This alone doesn't actually resolve our ambiguity. But when you go and you write the write your parser, you can write it using this style where you match the prefix at the same time. You don't treat them as two different productions. You treat them as one production that both share this prefix. And then in your parser, whenever you see an else keyword, you just continue parsing that one statement instead of stopping and treating it as an epsilon. So in code, the way that looks in code is you consume your if statement, consume the expression, consume the then statement, consume the statement, and then you just have an if statement that says, well, if my look ahead is an else, then just consume that and process the nested statement. That's all it looks like. And if otherwise, otherwise there was no else branch, and we can just move on and continue parsing the rest of our file. So all that rigmarole I went through with left factoring and all that really just reduces down to a pretty straightforward parsing function for that if statement. So you could put this inside of your statement if that's what you're already doing. You can separate it out to its own if statement. But yeah, that's how to resolve the dangling else in your program. Okay, so if we go back to our example, what ends up happening when we make that choice is we are at this point in parsing our grammar, and when we see this next if statement, we know that it's not an else branch, so we know that it must be part of the nested statement. Because it's not else, there was no else as the next look ahead, we know that it can't be part of our top level if statement. Does that make sense? Any questions on this? So when we see the next if statement, we know that we're parsing this nested statement. So it's followed by an expression, then followed by a statement. And then when we see this else keyword next in the input, we know that we can keep parsing our nested if statement. We know that this else is matched with this if statement. Yeah. Okay, questions on this? Question on this at all? Okay. So let's end it now. There's only 1 minute left, so let's end it here. And then next time we'll talk about the target language, talk about LLVM. And yeah, have a good night.